All right, welcome to my lesson on trapezoids and kites. I'm going to do this lesson in two parts because it's kind of long, so I'll do trapezoids first, and then don't forget to watch the second video about kites. We want to be able to recognize quadrilaterals. Up to this point, we've been studying parallelograms, and now we're going to look at two more kinds of quadrilaterals, trapezoids and kites. We want to be able to recognize them and apply the properties that we know about them to solve problems. We got some new vocabulary here. And all of this vocabulary here, this is all of our trapezoid vocabulary. This is best defined probably with a sketch. Okay. So here is a sketch of a trapezoid ABCD. And a trapezoid is a quadrilateral with exactly one pair of parallel sides. So, as opposed to a parallelogram where all these two, AD and BC, would also be parallel, here we have a quadrilateral with just one pair of parallel sides. These sides are called bases, and the non-parallel sides are called legs. The base angles are formed by a base and one of the legs. So here's a base angle, here's a base angle, but this is a base as well, so these are also base angles. All right, we're also going to talk about a specific type of a trapezoid, which is called an isosceles trapezoid. Now, you're probably familiar with the term isosceles in geometry. We've studied isosceles triangles. So it should make sense that an isosceles trapezoid is really just, I'm going to take this isosceles trapezoid and just extend these two sides. It's just an isosceles triangle that's had the top cut off. And in an isosceles triangle, you know that two sides are congruent. In an isosceles trapezoid, the two legs will be congruent. So if a trapezoid is isosceles, then we know both the legs will be congruent. It follows from what we know about isosceles triangles that the base angles will also be congruent. So these angles here will be congruent, but also these angles F and J will be congruent. And if a trapezoid has one pair of congruent base angles, we can recognize that immediately. Even if we know nothing about the length of the legs, if we know that it has a pair of congruent base angles, then we know it's an isosceles trapezoid. And if we have a trapezoid that is isosceles, then there's something else we know about it. Its diagonals are congruent. All right, let's take a look at an example here. Here, could we prove that these diagonals are in fact congruent? Well, if they tell us that ABCD is an isosceles trapezoid, let's mark all the stuff that we know to be true. We know AB is parallel to CD. The bases are parallel. If it's an isosceles trapezoid, we also know that the legs are congruent to one another. And if it's an isosceles trapezoid, we also know that the base angles are congruent to one another. And we can take a look at, we have a side here and an angle. And this side, DC, is congruent to itself. So now I'm going to highlight two triangles for you. I'm looking at this triangle ACD. And hopefully you recognize that that is congruent to this triangle DBC. And the reason we know that, remember from congruent triangles, side, angle, side, that's congruent to side, angle, side. If we know these two triangles are congruent, we know all of their corresponding parts are congruent because corresponding parts of congruent triangles are congruent. Remember that acronym, CPCTC. That means that AC is congruent to BD. Okay, let's try a couple of examples. Here we have each side of the basket shown as an isosceles trapezoid. Well, I'm going to mark that right away. What do I know about isosceles trapezoids? I know those are congruent. I know these angles are going to be congruent to each other, and these angles will be congruent to one another. I also know the diagonals will be congruent to one another. If the measure of angle JML, so this angle down here, is 130 degrees, I'll just label that, and KN equals 6.7 feet, and LN is 3.6 feet. Some of this information is not needed to find the measure of angle MJK, but we can do that anyway. They want us to find the measure of angle MJK, this guy in here. Okay. Well, hopefully you remember that, oh, there is one thing that I forgot to mark that we know about isosceles trapezoids. We know this about all trapezoids. These lines are parallel. And if these are parallel lines, we can look at JM as a transversal. And then what is the relationship between this angle KJM and JML? Those are consecutive interior angles. And what do we know about consecutive interior angles? If we call this angle X, we know consecutive interior angles, when the lines are parallel, are supplementary. These two angles have to add up to 180. So we can subtract 130 from both sides, and we get X equals 50 degrees. Okay. Now, could we find the length of these diagonals, MK? If this is an isosceles trapezoid, then we know the diagonals are congruent, and we also know that these are going to create congruent triangles here. This triangle is congruent to this triangle. And therefore, if this is 3.6 feet, then MN must be 3.6 feet as well. So how long is this diagonal MK? 3.6 plus 6.7 equals, what do we get there? 10.3 feet. Okay? All right. Let's take a look at another example here. Here again, we've got an isosceles trapezoid. The measure of angle FGH is 124 degrees. And they want us to find the measure of angle EFG. I'm going to highlight that in blue. This guy right here. Okay. Same thing. This is a trapezoid. Those are parallel lines. That makes FG a transversal. And the relationship between these two angles, let me give that 2 arcs. The relationship between these two angles, they are consecutive interior angles. We know when the lines are parallel, the consecutive interior angles have to be supplementary, which means they add up to 180. So we can subtract 124 from both sides. We're going to get X equals 56 degrees. Okay. All right. Let's take another look at the diagonals here. In this isosceles trapezoid, they're telling us that FI is 9.8 feet and EG is 14.1 feet. So I'm going to just draw this here so that we can see that this whole diagonal here is 14.1 feet. Could we find IH? Looking for this segment right here. Okay. Well, we know if it is an isosceles trapezoid, you know, the legs are congruent. We know the diagonals are congruent, and therefore I should be able to subtract 9.8. Well, let's call this X. We know that X plus 9.8 is going to have to add up to 14.1 for these diagonals to be congruent. And we can subtract 9.8 from both sides, and we get X equals 4.3. Okay. All right. Let's take a look at a little graphing. Here we have quadrilateral ABCD with these given vertices that have been plotted. They want us to show that ABCD is a trapezoid, and then determine whether it is an isosceles trapezoid. So we've got to prove whether or not it's actually a trapezoid. They're just telling us it's a quadrilateral. How could we determine whether or not this is a trapezoid? To be a trapezoid, we've got to have exactly one pair of parallel sides, the bases. And if you look at this, you probably suspect that maybe CD and AB are bases. How could we confirm that? Let's take a look at the slope of this line here. Going from B to A, I go up 1, 2 units and over, so I'm going to go up 2, rise over run, up 2, over 1, 2, 3, 4, 5, 6, 7, 8 units. 2 over 8, which you might recognize simplifies to 1 over 4. All right, let's check the slope of CD. Going from C to D, I go up 1 and over 1, 2, 3, 4. So, are these lines parallel? Yes, they are. I can mark them. I know I have a trapezoid. But how could I determine if it's isosceles? There's 2 checks we could do. We could check and see if the legs are congruent. Or we could check and see if the diagonals are congruent. How would we do that? Well, we're going to use our distance formula. The distance between any 2 points on the graph equals the square root of the change in x squared plus the change in y squared between them. Why don't we take a look at the distance from B to C? And let's say going from B to C, my change in x, I come over 1 unit and I go up 4. So my change in x is 1 unit and my change in y is 4 units. So this is going to be the square root of 17. Okay. Let's see if it's congruent to AD. Let's check the distance from point A to point D using the distance formula. My change in x going from D to A, I go over 1, 2, 3. Go over 3 units and I go down 3 units. So my change in x is 3 squared plus my change in y is 3. So this is going to be the square root of 9 plus 9, which is the square root of 18. Are these 2 legs congruent? Not quite. They're very close, but not quite. So this is not an isosceles trapezoid. All right. Next idea we have to look at for trapezoids is called midsegment term. And the midsegment of a trapezoid is parallel to each base, and its measure is 1/2 the sum of the lengths of the bases. And this is because the midsegment is located exactly halfway in between the bases. You'll notice it's marked. Point B is on the midpoint of AC, and point E is on the midpoint of FD. So it should make sense that this midsegment is going to be the average of the 2 bases. So I can say BE is going to equal 1/2 the sum of the bases, which is basically the average of the bases. That is the average of the bases. Okay, so if we know 2 of these, we can find the third using this formula. Let's try an example. All right, in this figure, MN is the midsegment of trapezoid FGJK. What's the value of x? Okay, we know the midsegment is going to equal the average of the bases. So we could say 30 is going to equal 1/2 times the sum of these bases, x plus 20. Now, could we solve that for x? Probably the fastest way to do that would be to multiply this entire equation by 2 to get rid of that 1/2. And we get 60 equals x plus 20. And if we subtract 20 from both sides, we're going to get 40 equals x. Now you might notice a pattern here. Since these sides are straight lines, there's going to be a linear relationship between how these segments increase in length. And so if we increase by 10 to go from the base to the midsegment, we're going to increase by another 10 to go from the midsegment to the other base. So you might recognize that pattern and you might be able to apply that in some problems. But don't forget, if you end up with a lot of variables in here and a lot of unknowns, don't forget, you've got to go back and use the algebra. Let's try one more. Here we've got an isosceles trapezoid with midsegment JK. Could we find XY if JK is 18? They're telling us this is 18 units. And WZ is 25 units. Okay, I'll call this X. So how would we find X? Now you might be looking at this and saying, oh, 25 minus 18, that's 7. So I'll go down 7 again, and I will find that X equals 11. Well, let's see if that's true. Our midsegment should be equal to 1/2 times the sum of the bases, x plus 25. Let's solve this for x and see if this in fact works. We can multiply both sides by 2 to get rid of the 1/2. We get 36 equals x plus 25. And if we subtract 25 from both sides, we get 11 equals x. Okay, that's our lesson on trapezoids. Don't forget to watch the second part about kites coming up next.